Hello, my dear students. Myself, Dr. Jatin Agarwal, and I welcome all of you on this 4Pi Academy. Here on this 4Pi Academy, we provide the best coaching related with CSIR NET GATE examination of physics. And apart from that, we also provide the best coaching for IIT JAM entrance examination. Right from today, we are going to start a series related with this very important topic, that is atomic and molecular spectroscopy. And in this series, we will discuss separately the atomic spectra, and then we will come to the molecular spectra. And our main aim of this series is to discuss all the important topics so which are part of the CSIR NET GATE syllabus. And apart from that, after discussing the topic, we will also discuss the important questions which come in the previous year examination. And in this atomic spectroscopy, we will cover this topic in 8 to 10 lectures. And I will start to discuss from Bohr-Sommerfeld theory of hydrogen atom spectra. And in this spectra, we will discuss the line spectrum of hydrogen and hydrogen-like atoms. And we will discuss in detail the Bohr theory of hydrogen-like atoms. And then we will cover the Rydberg constant and how this Rydberg constant which changes with the change in the atomic number of a nuclei. And after that, we will discuss the fine spectrum of hydrogen atom. And then we will discuss some coupling schemes such as LS and JJ coupling schemes, and which are then we will compare these coupling schemes with respect to atomic spectra and the nuclear spectra. And further moving in this lecture series, we will discuss some of the important effects such as Zeeman effect, why this happens due to the presence of magnetic field. And then we will discuss the normal Zeeman effect, anomalous Zeeman effect, and how this effect changes with respect to change in spin, and how further Paschen-Beck effect and the Stark effect, and how these effects which are related with the change in magnetic field. And then we will cover the very important topic of the line broadening, scattering, and how this spectra of line broadening it happens with respect to natural broadening, and then how it changes with the Doppler effect. And in the last section of this atomic spectroscopy, we will discuss some of the selection rules for this various multipole transitions, and then we will discuss how this electric and magnetic transitions so they change with respect to quadrupole movement and magnetic movement. So first of all, in this today's lecture, I will discuss the atomic model, and I will start with the Thomson model and how this idea of a Bohr atomic model it comes in the mind of Bohr. So basically, this atomic models discussion has been started in the year around 1900. So after the discovery of electron, which has been discovered by J.J. Thomson, and the discovery of radioactivity which has been discovered in 1897. And Thomson, what he has explained in this model, which we also known as the Plum pudding model. So what Thomson said that the electrons, so let me choose this pen. So the electrons, so suppose this is the structure of atoms, the negative charge particle and the positive charge particle, so they are present randomly within the atom, and this model we also known as the Plum pudding model. So this J.J. Thomson proposed this atomic structure, and he assumed that the atom consists of electrons which are distributed in the positively charged sphere of a radius that is around 10 raised to power minus 10 meter, that is the radius of atom. So but this model was not successful because it could not explain all the features of this optical spectra of hydrogen, and why the spectra changes with the change in atomic number, and why the spectra of hydrogen and helium, they are different. So later in the year 1911, Rutherford explained a model which we generally known as the Rutherford alpha scattering experiment. So what basically Rutherford was doing, he was bombarding some radiation to some atomic structures, and what he has observed that so there is some sort of scattering which has been happened. So he observed that the scattering is maximum in the center of atom, and suppose he is bombarding this radiation, and so these radiations, they are scattered at an angle of 180 degree, and the radiations, so they are getting scattered something like this. So they are scattered at different angles. So but in the center, when he shoot out these radiations, so the radiations, they get scattered at an angle of 180 degree. So from that he observed that there is some sort of some positive structure, positive charge structure, which is present within the center of the atom, and he called this structure as the nucleus. So he explained in his model that the positive charged particles, they are present in the center, which he explained it as a nucleus, while the negative charged particles, they are present in rest of the atoms. And he explained that this positive charge structure, which is of the order of 10 to the power minus 15 meter. But this model also did not got successful because it did not explain the stability of the atom and why the energy distribution to atom is a discrete energy distribution. Then in the year 1913, the scientist Niels Bohr, he modified this Rutherford model, and he developed a theory by constitution of atom. And what he said, that he used the quantum theory of radiation, and which has been developed by Planck and Einstein. So Bohr model was successful because he successfully explained the energy distribution for different energy orbits, and some of the limitations of the Bohr model, it has been explained by Sommerfeld model, and then the Sommerfeld model has been modified by the vector model of the atom. So this is the latest model which we generally use these days. So I will discuss all these models step by step. So starting from the very first point, so what is this atomic spectra? So the atomic spectra is the atom has various energy levels. So if the atom makes a transition from either a less excited state to a higher excited state, you can see here, so the atom which is present in the higher excited state, and it is going to lose its energy and comes to the lower excited state, or it can have a transition from a lower energy level to a higher energy level. So in this process, atom produces radiation, and the collection of radiations, it has been explained by the atomic spectra, कि जो absorption के थ्रू जो ट्रांजिशन होती है या emission के थ्रू ट्रांजिशन होती है, वो एक तरह से हम स्पेक्ट्रम के फॉर्म में ऑब्जर्व कर देते हैं. सो एटॉमिक स्पेक्ट्रा है जो इट इज ऑफ टू टाइप्स. सो फर्स्ट वी जनरली कॉल इट एज द अब्जॉर्प्शन स्पेक्ट्रा, कि जब कोई लाइट जो है वो अब्जॉर्ब कर ली जाती है, कि ਜਦੋਂ कोई ਜਿਹੜੀ लाइट आ it is being absorbed. For example, the electron which is present in the ground state of this electron, now when this electron it absorbs some sort of a light which is being striking on this atom, and it goes to the higher state. So उस केस ਦੇ ਵਿੱਚ ਜਿਹੜਾ स्पेक्ट्रम ਆਂਦਾ ਹੈ ਉਹਨੂੰ ਆਪਾਂ absorption spectra ਕਹਿ ਦਿੰਦੇ ਹਾਂ. So absorption spectra is something like this. So suppose the energy of the electron which is in the ground state is EI, and when it absorbs some sort of light and it reaches to the final state which is known as the EF state, and the difference in energy, that is the delta E, which is EF minus EI, that is of the order of h nu, and this h nu we can find the wavelength, change in wavelength from that change in energy, and this wavelength we generally observe in this visible light spectrum, and you can see that there are some sort of dark lines ਜਿਹੜੀਆਂ ਸਾਨੂੰ dark lines ਜਿਹੜੀਆਂ ਇੱਥੇ ਦਿਖ ਰਹੀਆਂ ਆ. so what they are showing, so they are showing the absorption of wavelength of that particular region. And similarly, so in the emission spectra, so when the atom or electron which is in the higher energy state, and when it loses some of its energy in the form of a photon, it is emitting some photon and it comes to the ground state. So us case ਦੇ ਵਿੱਚ ਜਿਹੜੀ ਕਿੰਨੀ wavelength ਦੇ ਵਿੱਚ change ਹੋ ਰਹੀ ਆ, so it has been observed through these bright lines. So generally absorption spectra, it is in the form of dark lines, while emission spectra, it is in the form of bright lines. And you can see that these lines, so they are showing that this particular wavelength of light, it has been emitted by that particular electron when it is coming from the higher energy state to lower energy state. And one point I would like to explain, that the difference between the atomic spectra and the molecular spectra is, in atomic spectra, so there is a line spectra. So you can see that these are quite prominent lines. So this is purple line, this is blue line. So atomic spectra represent the line spectrum, while the molecular spectra, it is generally a band spectrum. And for example, if you are observing some sort of a band in that particular wavelength region in your screen, and from that band you can see that, so there is the emission which is happening in a molecule rather than an atom. So band spectrum, it is the representation of the change in energy for a molecule, while the line spectrum, it is the representation of a change in energy for a atom. Now starting with the Bohr atomic model, so Bohr considered 3 postulates in order to explain his model. Now Bohr used the Planck quantum theory to explain the emission of radiation. Now before discussing the Bohr atomic model, I would like to discuss the Planck quantum theory. Now Planck explained 2 points. So what he said, an electron can exist in one of the many discrete quantum states having definite value of energy. सो प्लैंक्स ने की किया कि इलेक्ट्रॉन जिहड़ा एक पर्टिकुलर एनर्जी जिहड़े आ ऑर्बिट्स दे विच जिहड़ा लाई करदा आ एंड वो पर्टिकुलर ऑर्बिट्स दे विचों जदों अपनी पोजीशन चेंज कर रहा है कितनी एनर्जी लूज कर रहा है या कितनी एनर्जी गेन कर रहा है सो उस एनर्जी तो आपां फाइंड आउट कर सकते हैं कि जिहड़ा वो डिस्क्रीट एनर्जी डिस्ट्रीब्यूशन या ओदी ऑर्बिटल स्टेट की है. सो दिस इज द फर्स्ट explanation of Planck's quantum theory. So second explanation is no emission of radiation will takes place if the electron remains in a particular quantum state. And if the electron jumps from one quantum state to another quantum state, only then the absorption or emission of radiation takes place. Emission takes place. On Planck की कह रहा है, so I will explain here. So suppose this is some sort of discrete quantum states of electrons, so which lie in a atomic structure. Now what Planck says, if the electron which is present in this particular quantum state, and if it changes its position, so for example if this electron it is going from this point to this point in the same quantum states, so उस केस दे विच की है कि इलेक्ट्रॉन दी जिहड़ी एनर्जी आ वो सेम रहेगी, एक पर्टिकुलर क्वांटम स्टेट दे लई जिहड़ी एनर्जी आ ओदी सेम रहेगी. And suppose one electron it is in this quantum state, and when this jump from this quantum state to this quantum state, now it has changed its quantum state. So in this case the energy of that electron it will change. So how much change? So that we will discuss. ਜਿਹੜੀ एनर्जी रिप्रेजेंटेशन बोहर ने दसी सी. सो उस केस दे विच वो कह रहा है कि अब्जॉर्प्शन ते एमिशन स्पैक्ट्रम उदों ही जिहड़ा आ आपां स्पैक्ट्रो साडे स्पैक्ट्रम दे विच आएगा कि जदों जिहड़ा इलेक्ट्रॉन आ इट इज चेंजिंग इट्स क्वांटम स्टेट. So these all are representation of quantum states. So these are some of the explanation of Planck's theory, and what he said that कि कितनी energy change हो रही है, so that is equal to E is equal to H into nu, and how much wavelength it has been changed. So from that we can calculate how much energy it has been changed. So next, what are the Bohr's three postulates? So Bohr theory is based on this Planck's quantum theory, and he considered three postulates. So first postulate of Bohr is, so Bohr assumed that an electron revolves in certain allowed circular orbits about the nucleus under the action of a nucleus force. So for example, this is our atomic structure. So there is the nucleus having charge plus Ze, and suppose this is our electron, it is revolving around this nucleus with a velocity v. So the charge on the electron is this, and mass of the electron is me, and this is the difference, or you can say the atomic radius, that how much at a distance the electron lie from the nucleus. So the force of attraction between this electron and this nucleus, it has been explained by the Coulomb's law. Now what this Coulomb's law says, 1 over 4 pi epsilon naught Z square over R square, where R is the electron nuclear distance and Z is the atomic number. And for hydrogen we will take the value of Z as 1. and epsilon naught here, it is the permittivity of free space, and now this electron, it is revolving in a circular motion, and the circular force which is acting on this, that is known as the centripetal force, and the value of the centripetal force is mv square over r. So these all we know. So when a body is revolving in a circular motion, and why this body is lying in this circular motion, that is due to the centripetal force, so which is binding this a particle in a circular motion. And when we compare these two equations, and from that we can find the velocity of the electron, with which velocity this electron, it is being revolved in that particular orbit. So that is 1 over 4 pi epsilon naught z square over r square, and from that v square, it is coming out to be 1 over 4 pi epsilon naught z square over m into r. So this is the first postulate of the Bohr, कि जड़ी Coulomb force जड़ी है, that is equivalent to the centripetal force, and from that we can calculate the velocity of the electron in a particular orbit. So the second postulate Bohr considered is Bohr assumed that the hydrogen atom may be stated as only those circular orbits for electrons for which the angular momentum is equal to the integral multiple of h over 2 pi. So angular momentum is the integral multiple of h over 2 pi, where n represents the number of orbital, कि किहड़े ऑर्बिट दे विच जिहड़ा इलेक्ट्रॉन लाई करदा है, सो उहदे अकॉर्डिंग जिहड़ा है उहदा एंगुलर मोमेंटम जिहड़ा है आपां कैलकुलेट कर सकते हैं, एंड द वैल्यू ऑफ दिस n, it varies from 1 to 3 and so. And second, the orbital angular momentum, we know that when a body is revolving in a circular motion, the orbital momentum, angular momentum, that is represented as L, that is the linear momentum multiplied by the radial distance. So we can generally write it as mv into r. And when we equate these two equations, and from that we can calculate mvr, that is equal to nh over 2 pi, and from that we can find the value of this radius, कि केड़े ऑर्बिटल एंगुलर मोमेंटम दे विच इलेक्ट्रॉन है ते ओदा रेडियस जिहड़ा है वो कितना होएगा. So that is this much. So let us say this is our second equation. And the third postulate, Bohr considered that a quantum of energy is radiated only when an electron jumps from higher energy orbit to the lower energy orbit, and the frequency of emitted radiation, it is proportional to the difference between two energy states. Now suppose we have these two energy states, and when an electron, suppose this is EF, this is EI, or you can say this is E2 or this is E1, and when this electron, it is jumped from the higher energy state to the lower energy state, and the change in frequency, that is equal to the difference in energy of these two states. So because E2 is higher, so here we consider E2 minus E1. So these are the three postulates, so which Bohr discussed, and from that we can calculate what is the value of this Bohr radius. Now the value of the Bohr radius that is coming out to be, I will discuss right here. So we know that mv square over r, that is equal to the force of attraction 4 pi epsilon naught z square over r square, and m square v square r square, so that comes out to be 1 over 4 pi epsilon naught z square r into m, and from that we can say nh over 2 pi square, so that is equal to 1 over 4 pi epsilon naught z square into r into m, because mvr, this is our orbital angular momentum, and this is equal to nh over 2 pi, that is from the second postulate, and from that we can calculate the Bohr radius, the value of atomic radius for a particular orbit, n square h square epsilon naught over 4m z square. So this is a very important relation. So the numerical from this relation, it can come generally in the exam. So this is the same form which we have derived in the previous slide. Now the value of this Bohr radius, it is directly proportional to n square. So that is the radius of, for example, the second orbit, it is 4 times that of the first orbit. Now kinetic, we have to find the total energy of the electron, so that is the sum of kinetic energy plus potential energy. Now kinetic energy, that is equal to half m v square. So the value of v we have derived from the first Bohr postulate, so it is nh over 2 pi mr whole square, and it is coming out to be 1 by 2 m n square h square over 4 pi square m square into r. Now putting the value of this atomic radius, so we can calculate the kinetic energy. It comes out to be me square z square over 8 epsilon naught h square over n square. And similarly we can calculate the potential energy. So potential energy we know that is 1 over 4 pi epsilon naught Zd, that is the charge of nucleus, minus E, that is the charge of electron, over the difference between these two, that is Rn, and it is coming out to be minus me square z square over 4 epsilon naught square h square over 1 over n square. So when I put the value of this r, and what we get is, we get this relation. So this is the value of potential energy, and from you can compare that the value of kinetic energy, it is greater than the potential energy of the electron, and the total energy, that is the sum of kinetic energy plus potential energy, and it comes out to be minus m e the power 4. So here, sorry, it is m e the power 4. So it is minus m e the power 4 over 8 epsilon naught square ch cube hc z square over n square. And this energy for the nth orbit, it comes out to be minus r infinity hc z square over n square. Here r is known as the Rydberg constant, and whose value is equal to m e the power 4 over 8 epsilon naught square ch cube, and putting all these values, and it comes out to be 1.0974 into 10 to the power 7 meter inverse. And similarly, once we find out the value of this energy, that is minus r infinity hc z square over n square, so you can see that the energy, it is directly proportional to z square over n square. So what does it means? It depends upon the atomic number of the atom, what atom we are talking about, and in which orbit this electron it is present, whose energy we have to calculate. And for hydrogen, so for hydrogen atom, so whose Z is equal to 1, and the value of En, it is coming out to be Hc over n square, that is minus 13.6 over n square electron volt. And for the first orbit, so this energy is different for different orbit, and for the first orbit its value is minus 13.6 electron volt. And similarly, you can calculate the energy for second orbit, and it comes out to be 13.6 divided by 4, so that is minus 3.4 electron volt. And you can see that this energy is being increased with the increase in orbit, and the value of energy for the infinite orbit, that is 0 electron volt. From that we can derive the relation of this energy with respect to the wavelength. Now the third postulate says h nu, that is equal to E2, that is the energy of electron in the second excited state minus energy in the first excited state, and putting the value of this E2 and E1, so it is r infinity hc z square over n2 square minus r infinity hc z square over n1 square, and it comes out to be h nu, that is r infinity, so take the common things outside, 1 over n1 square minus 1 over n2 square. So these signs get changed because this minus and minus, this get plus, so we have taken this plus sign at the first place and this negative at the second place. Now for hydrogen atom, so Z is 1, and the frequency we know that is equal to C over lambda, and putting the value, so Hc, that is equal to Hc over lambda, that is r infinity hc z square 1 over n1 square minus 1 over n2 square, and this hc get cancelled, and what we have derived is the relation of the wavelength, that is how the wavelength it is being changed when an electron it jump from one orbit to another orbit. And this is a very important relation in order to find the change in energy, in order to find the change in wavelength when electron it is changing its position from a one orbit to another orbit. So the last topic for today's lecture, so that is how we can calculate the time period and frequency of revolution. Now the time period of revolution generally represented with T, so that is equal to 2 pi r, that is the circumference of an atom, that is equal to 2 pi r divided by v, that is the velocity of that electron in a particular orbit. Now the value of this atomic radius, this we have derived, that is n square h square epsilon naught over pi m z square, and similarly from the first postulate we have derived the electron velocity for a particular orbit, that is 2 epsilon naught nh. Now putting the value of this r and v in this equation, what we get is 4 epsilon naught square n cube h cube over mz square e raised to power 4. So this is the required expression for time period of electron in the nth state, and for a particular state we can calculate the time period for that state, and from this time period we can calculate the frequency of revolution, so with which frequency that electron it is being revolved in that particular orbit. So that is the inverse of time period mz square e raised to power 4 over 4 epsilon naught square n cube h cube, and we know the Rydberg constant, so this equation comes out to be 2 r infinity, that is our Rydberg constant, divided by n cube. So this is the frequency of revolution of electron in a particular orbit. So this is also a very important relation in order to find out the time period or the frequency of electron for a particular orbit. So related to these two discussion, we will solve some of the numerical problems. So first problem we are going to discuss, that is an electron is initially in n is equal to 3 state, and the average lifetime of this state is 10 raised to power minus 8 second. The number of revolution that the electron take place before making a transition to n is equal to 2 state. Now what the question says, the electron is in the n is equal to 3 state, and it is transition from n3 to n2 state. So suppose this is equal to n3 and this is equal to n2 state, and the lifetime of that electron in that particular state, so which generally represented as tau, that is minus 8 second, and we have to calculate the number of revolutions. So in order to find the number of revolutions, we need to find the frequency of revolution of the electron in that particular state. Now n is equal to 3 it is given, and the average lifetime in that state, that is minus 8 second, and the number of revolutions, so that is equal to frequency of revolution multiplied by the average time in that particular state. and it comes out to be Fn into 10 raised to power minus 8. So this we have to find, and now we have to find the value of this Fn. Now the formula which we have discussed, that is equal to frequency of revolution is equal to 2r infinity c over n cube. Now the value of this Rydberg constant, so that is equal to 1.097 into 10 raised to power 7 meter inverse. And in the next lecture we will also discuss how this value of Rydberg constant it changes with the change in atomic number of a atom. So ਉਹਦੇ ਤੋਂ ਇਲਾਵਾ ਆਪਾਂ ਜਿਹੜੀ ਸਪੈਕਟਰਮ ਲਿਮਟ ਹੈਗੀ ਆ, ਸੋ ਵੇਰੀਅਸ ਟਾਈਪ ਆਫ એનર્ਜੀ ਸਪੈਕਟਰਮ ਹਾਈਡਰੋਜਨ ਦੇ ਆਪਾਂ ਜਾਂ ਹਾਈਡਰੋਜਨ ਲਾਈਕ ਐਟਮਸ ਦੇ ਜਿਹੜੇ ਆ ਉਹ ਆਪਣੇ ਅਗਲੇ ਲੈਕਚਰ ਦੇ ਵਿੱਚ ਡਿਸਕਸ ਕਰਾਂਗੇ. ਸੋ solving this problem, putting the value of this Rydberg constant, and c is the speed of light. So we consider that it is moving with the speed of light. N is 3 and the frequency it comes out to be 6.6 over 27 into 10 raised to power 15 hertz. And from that we can calculate number of revolutions. Number of revolutions, that is Fn 6.6 over 27 into 10 raised to power 15 into 10 raised to power minus 8, and it comes out to be 2.4 into 10 raised to power 6. So our right option is option C. So similarly you can solve other questions. So if the time period of electron in that particular orbit it has been asked. So moving to the next question. So the question is the energy required to remove an electron from a single ionized helium atom which is in the 8th orbit. So n is equal to 8 it is given. So we have to find the minimum energy required to remove an electron. So what is the binding energy? So binding energy is the minimum energy required to remove an electron from that particular orbit. So the single ionized helium atom. So here the atom is helium. So whose atomic number is 2, mass number is 4. So the value of Z, that is 2, n is equal to 8 is given, and we know the energy of electron in a particular orbit. So that is equal to 13.6 n square into z square. Here putting the value of z and n, so it comes out to be z is 2, 2 square is 4, and 8 square is 64, and it comes out to be minus 13.6 over 16, that is minus 0.85 electron volt. So this will be the energy of the electron in that particular orbit. Now what we have to calculate is, we have to calculate the binding energy or the minimum energy required to remove the electron, and this binding energy is, that is minus of the energy of the electron in that particular orbit. So putting the value, so which we have derived, so it comes out to be plus 0.85 electron volt energy is required if we want to remove that helium atom, which is, if we want to remove an electron from this helium atom from that 8th orbit. So next question, the last question is the momentum of the photon emitted by a hydrogen atom making a direct transition from an excited state n is equal to 10 to the ground state. Now the electron, it is present in 10th state and it is losing its energy to the ground state, and we have to calculate the momentum of this photon. We know from the de Broglie hypothesis the momentum that is equal to h over lambda, and once we able to find the value of this wavelength or the change in wavelength, from that we can calculate the change in momentum for that particular electron for this type of transition. Now we have derived this formula, so n is equal to 10 is given, so we know that 1 over lambda, that is equal to r infinity 1 over final state minus 1 over Ni, that is the initial state. So R infinity, that is equal to 1 over final state. So final state जिस point ਦੇ ਉੱਤੇ ਉਹ ਆ ਰਿਹਾ ਹੈ, that is the first state ਦੇ ਵਿੱਚ ਆ ਰਿਹਾ ਹੈ. Initial state, that is it is in the 10th excited state. So putting the value of this Rydberg constant, so this comes out to be 99 over 100 1 over lambda. So you can write here lambda, that comes out to be 100 over 99 into 1 over r infinity. So putting the value of this Rydberg constant, that is 1.097 into 10 is to power minus 7, and the wavelength comes out to be 0.92 into 10 is to power minus 7 meter. So once we find the value of this lambda, from that we can find the value of this momentum. So that is h over lambda. Now the Planck's constant value is 6.62 into 10 is to power minus 34 joule second over 0.92 into 10 is to power minus 7, and the value of P, it comes out to be 7.2 into 10 is to power minus 27 kilogram meter second inverse. So this will be the energy of the photon which will be emitted when an electron which is losing its energy from the 10th excited state to the ground state. So I hope you have enjoyed this lecture and you have followed all those important relations which I have derived for this Bohr atomic orbital, and in the next lecture we will discuss all the energy limits, how the spectrum changes with respect to change in wavelength, and we will also derive how the change in atomic number, the Rydberg constant, it is being changed, and we will talk about the fine and the series limit of a hydrogen spectrum, and related problem we will also discuss in the next lectures. So till then, goodbye and keep watching 4Pi Academy. Bye.